אוקיי, אפשר לסכם? מעולה. With Nizar's help now, I know that you're all so excited to see the movie that we were not able to see on Thursday. With Nizar's help now it should be working. So we will start. We'll start class with watching this short movie from the paper of Yitzhak Fried. As always, no one remembers the first author who did all of the work, and we will discuss it and then go back to the Hopfield model of associative memory. So what you're going to see is the firing of a single entorhinal cortex neuron in response first to watching short video episodes and then thinking about these video episodes. Okay? You're with me? Okay. So beeps would correspond to the spikes. You will not be able to. So this is a Hollywood sign. Martin Luther King, I have a dream. Not too much response. Madonna.
Auditory and visual together?
No. Okay. So the patients watched the clip. Because of copyright, you will not be able to watch it, but you can.
It's only visual?
No. It's visual and auditory. It's an entire clip.
And where is the neuron?
This is entorhinal cortex. But for the purpose of our discussion, we don't care. It's a neuron. Okay, Simpson. Again, Martin Luther King. Who cares? Okay, pyramid. Too dangerous to visit anyway. Nothing. Again. I have a point here, right? This neuron is specific to Michael Jordan, whatever. Okay, so the point here is not that this neuron is responds only to the Simpsons or to this particular clip. Nor this is the case that this is the only neuron in the brain that would respond to the Simpsons. That's not the point. The point is there is some selectivity here. And out of the 7 or 10 different clips, this neuron responded preferably to the Simpsons. Yeah.
Did someone volunteer to take notes today?
Yes. Okay, so this is the point of the first part, that there is selectivity in these neurons. Now, and this is a really interesting part, the subject, the patient, was asked to recall the episodes. Basically, what did you see? Okay? So I think that I think it's pretty exciting. So the idea is that the representation in the brain while you observe something is similar to the representation while you think about it. And the selectivity which allows us to actually see it. And now we are trying to come up with a model that in some sense has this property. And this is a Hopfield model. And I'm happy to see that much of it is on the screen, which will save me some time. So the idea in the Hopfield model is we have this set of equations, the standard model, and we would like to embed memory patterns in this model such that the attractors of these dynamics would correspond to the embedded memory patterns. So what is what's a memory pattern? A memory pattern is a pattern of activity in the network, a particular pattern of activity in the network. And we would like to construct a connectivity matrix such that these memory patterns would be the attractors of the network. Preferably, these would be the only attractors. This will eventually not happen in this model, but this would be the goal. The Hopfield model. In the Hopfield model, the connectivity matrix is proportional to the sum of the correlation of pre- and postsynaptic activities summed over all the memory patterns. And if we think about a mechanism that can generate such a connectivity matrix, one possible mechanism is the following: we force the neurons in the network to have a particular pattern of activity, and we change synaptic connections such that synapses between neurons whose firing rate is similar increase the strength of connectivity between them, whereas neurons that have different that fire very differently, the synapse between them will become weaker. It's a way of implementing this particular connectivity matrix. Questions? Now, because of the nonlinearity, finding the fixed points in this set of equations with this connectivity matrix is complicated. So what we will do is the following thing. We will start by considering the case of beta going to infinity, and we will look for fixed points of this set of equations in this limit. Or more precisely, I'm going to ask what are the conditions such that these memory patterns are in fact fixed points of these dynamics. This is what I'm going to do. I'm not going to prove that these fixed points are stable, although from the equations you will get a feeling of whether they are stable or not. And after understanding this, we will consider the contribution of beta and look at the dynamical equations. Questions? So basically all these things we did last week. Okay, so my goal My goal is to prove to you, or to study the conditions under which these memory patterns are fixed points of the dynamics. So how am I going to do it? So at the fixed point, the activity of neuron I should be the sign of the input to this neuron, which would be just sum over j of j, j, s, j. Now, the more precise question is if these activity patterns, Sj, correspond to a memory pattern, will Si correspond to the activity of the ith neuron in this memory pattern. Is this point clear, or should I repeat it? Yeah. So what's the meaning of a fixed point? Of a memory pattern being a fixed point? The meaning is that if I force all neurons in the network to be in this state, now if I remove the external input, they will stay in this state. When will this happen? This will happen if, let's think about the first memory pattern. Let's consider, for simplicity, the first memory pattern, P1. So P1 is a fixed point of the dynamics if the activity of neuron I if the activity of neuron I is equal to the desired activity given neuron 1, provided that all neurons in the network are forced to be at the activities of all neurons in the network are as required from this memory pattern. Yes?
But the stimulus doesn't have to be the exact memory. It's going to be just close enough to it so that it converges to the memory.
Maybe, but I'm studying the conditions for the first memory pattern to be a fixed point. This is the question I'm asking.
Yes, but you said like if I would give a stimulus, it would stay because it's a stable fixed point. But you can also start not at the fixed point.
Right, but this is a more or less well-defined requirement. So I want to be precise here. So I want to ask whether this memory pattern is a fixed point. You could also argue that out of the 10 to the 11 neurons in the brain, if all of them but one have the desired activity, this is good enough. If one of them is doing whatever it wants, it will not matter in the sense of a memory pattern, but this is more complicated. So I'm asking the question, what are the conditions such that this one, that the first memory pattern, and because of symmetry I can ask this question for all memory patterns, will be a fixed point of the dynamics. And this is the requirement for the first memory pattern to be a fixed point of the dynamics. Is this point clear? It's kind of obvious. I don't know why it's taking me so long to explain it. Okay. So how are we going to address this question?
Solve it.
To solve what?
So J, I, J, summing.
Okay. So let's see how we're going to do this. It's not easy to be a university professor. Okay, so the question that we ask is whether this equation is satisfied, basically. So another way of rewriting this equation is to multiply this equation by pi1. Excuse the queen. So I'm multiplying this equation by pi1. So pi1 squared is equal to 1. This is equal to pi1 times sine of sum over j, jij, pj1. Or I can just...
pi1 is defined with 1 over n? pi is defined with 1 over n?
No, it's 1 or minus 1.
So it should be n. It should be n, not 1.
Not the vector.
It's not a vector, it's a scalar.
Why is it 1 and not
N.
1?
Wait,
One by one.
Oh, it's 1 of the components. Okay.
But this should be true for every
Component. Okay.
this is for every I.
Oh, okay.
For all I. Now there's another question here. Okay, good.
Sorry, could you please not cover the definition of the model because it's really confusing. Thank you.
For the time being.
Yes. Okay.
For the time being. Or rewriting it, I can just argue that one of the requirements would be that one would be equal to the sine of pi1 times sum over j, jij, pj1, right? So pi1 is just plus or minus 1, so I can enter inside the sine function. Or another way of writing it is to say that the requirement is that pi1 times sum over j, jij, pj1 should be larger than 0 for all neurons I. This is a requirement that for P1, the vector P1 to be a fixed point of the dynamics. Because it's a sine and Pi1 is plus or minus 1. If it's plus 1, then sure, no problem.
Okay.
If it's minus 1, then it would be just sine of minus, which would be minus of the sine. No.
That's fine.
That's fine?
That's good enough.
Okay, it's good enough?
Yeah.
Thanks. I appreciate it. Okay. So this is a requirement, the thing here that you don't see. So the next step would be to replace jij with this definition that you like so much. Okay? So we're interested in Pi1 times sum over j. Jij is just equal to 1 over n sum over mu pi mu pj mu, this is jij, times pj1. So we are interested in this quantity, in the sign of this quantity. Right? Well, not exactly. This is j j that is not equal to I, because we said that ji is equal to 0. It's not very important. Okay, next step is to look at this sum and realize that there are two components here. One in which mu is equal to 1, and one for which mu is not equal to 1. So I'm going to rewrite this sum separately for mu being equal to 1 and mu not being equal to 1.
And the pj1 doesn't enter the sum, right? It's not. Don't sum it over j. How you do it?
No, this is jij, so the jij became sum over mu.
Oh, and the j is over j also.
Okay. Yeah, behind this you have hi is equal to sum over j of jij of j, but I'm the only one that can see it. Okay, so next step is this is equal to pi1 sum over j, not j is different from I, 1 over n, and here I have pi1 pj1 plus sum over mu larger than 1, pi mu pj mu sum over j pj1. Right? Okay. So let's look at the terms here. So here we have sum over j, pi1, this is not part of the sum is over j, pj1, pj1.
1.
Almost. We have sum over how many terms?
Oh,
n minus 1 terms. So this sum would give us n minus 1 over n times pi1, and pi1 times pi1 is 1. So this would be equal to n minus 1 over n. This is a contribution of the first term, plus sum over j, difference from I, 1 over n, sum over mu larger than 1, and here we have pi1, pi mu, pj mu, pj1. Right?
Can you ask if you write the mu more different than the 1? Because it's really hard to distinguish.
The mu and the 1.
Yeah. Thank you.
Questions? Are there any questions? Okay, let's look at the first term. That's easy, right? So the first term is equal to 1 minus 1 over n, which is approximately equal to 1 when n is large. Plus 1 over n. What can we say about this sum? How many terms do we have here? How many terms do we have here?
Mu minus 1 times.
What's the u?
Depends on how many memories.
Depends on how many memory patterns. So let's say that the number of memory patterns You will hate me for that, but you hate me anyway, so why should I care? I'm going to denote the number of memories with a capital P. Yes. Capital P. Okay, so how many terms do we have here? P minus 1 times n minus 1. So this is a sum of n minus 1 times p minus 1 terms, right? What can we say about this product?
Either minus 1 or plus 1.
So it's either minus 1 or plus 1. Why? Because all components here are either plus 1 or minus 1. So this is a product of 4 numbers which are either plus 1 or minus 1, so this product should be plus 1 or minus 1. Right? So far, so good. What else can we say about this product?
Random or
The average
so let's write it this. Okay, so I'm going to write it as a sum of k terms. K going from 1 to n minus 1 times capital P minus 1. So these are all the terms here. And I have here ZK. ZK is a product, is this product. What can you say about the distribution of ZK?
normal.
Who said normal? How can ZK be normally distributed if it's a result of a product of plus and minus 1? So it's either plus 1 or minus 1, so it cannot be normally distributed. If P is odd, capital P. Well, there are just 4 numbers here.
Uniform.
Uniform.
but
How can it be uniform?
But it is uniform.
How can it be uniform if it's only plus 1 or minus 1? It's a Bernoulli.
But the sum.
okay.
But is it really a Bernoulli? What's the probability of a plus 1 and minus 1 here? Why? Maybe it's 60.
50-50.
But 1 is 50. Well, we have 4 here.
But there's no
Are they
memory.
dependent?
Yeah, they're independent.
How do you know that they're independent?
Because every memory is independent.
Well, let's see. So we have I and j are independent, right? Because the sum is over j not being equal to I. And mu and 1 are independent
Because they're different memories.
because mu is larger than 1. So all these 4 numbers are plus or minus 1 with a probability 1/2, and they're uncorrelated. So zk is plus and minus 1 with a probability 1/2. So zk is equal to plus or minus 1 with probability 1/2.
This is not called uniform?
No, this is Bernoulli. Uniform is it's a continuous.
The uniform code. Okay.
No, uniform is something else.
Okay.
Uniform is something that is continuous between two values. Okay. Fine, whatever. So, but we don't care about all these minor and uninteresting details. All we want to know is whether this is positive or not. Is it positive or not? If it's positive, we are happy. If it's not positive, we are unhappy.
What is
Goes
the
to
whole
0.
sum or what?
This thing, we started with this requirement. Blah, 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 blah. This we continued to this requirement. Oh no. Okay. So this is drama. I'm too excited. So we want this to be positive, which means that we want this to be positive, which means that we want this to be positive, which means that we want this to be positive.
All 0.
Non-negative.
No negative.
Well, we have to say what sign of 0, but let's not worry about it. Let's say that we want it to be positive. So What are the conditions for which this would be? Will this be positive at all?
N needs to be bigger than 3.
N?
Needs to be bigger than 3.
Well, we're in the limit of large n. So will it always be positive?
No. It will approach 0 for high n, no?
What's the relation between
For
N
high.
and P?
Well, what should the relation between n and p be?
The sum will.
So let's say that p is equal to 1. Let's just for the sake of argument say that p is equal to 1.
So no sum.
Well, then it's okay, right? Then it's positive, then it's equal to 1 minus 1 over n, which is positive for n being larger than 1. Okay? So we are fine. Okay, so it seems okay if we want to store a single memory pattern. So if p is equal, if capital P is equal to 1, then we are fine, and this memory pattern is a fixed point of the dynamics. What about p? What will happen if p is equal to 2?
Should be 0.
High probability will be fine.
Okay. So let's see. If p is equal to 2, we have a sum of n minus 1 terms here. And these n minus 1 terms can be either plus 1 or minus 1 with some probability. Only in the rare case where all these zk's are equal to minus 1, then there might be a problem. But the probability of this would be very low. What about p being equal to 3?
Even smaller probability.
No.
No,
Will be larger.
Smaller probability that everyone will be negative 1.
Well, no, that's exactly the same probability
You
because
don't need all of them to be.
you don't need all of them.
Okay.
So will it work for p being equal to 3?
What's the problem?
Well, if p is equal to 1, then this is 0, we're fine. If p is equal to 2, then there are n minus 1 terms here. And if all zk's are equal to minus 1, then we have 1 minus 1 over n minus 1 minus 1 over n, so this would be equal to 0. So we may have a problem here, but the probability for this is very small. How small is it, by the way? What's the probability that all will be minus 1? So let's vote for it. That's how we prove things in math. 1 over n squared.
What? No.
Well, that was one suggestion. I want to
Half
vote.
over n minus 1.
Half over n minus 1.
No. Half. No, in the power of n minus 1. I mean. Yeah.
More suggestions? Somebody said something about factorial. You're not standing. So the right answer is this one. So what's the probability that one of them would be equal to minus 1? 1/2. 2 of them, 1/2 times 1/2. 3 of them, 1/2 times 1/2 times 1/2. N minus 1 of them, 1/2 times half times half. N minus 1 times. Okay, good. So, but this was the case for n being equal. So the probability is very low in the limit of n of large n, so we don't worry about it. But what about p being equal to 3? Or 4? Or God forbid 5? What can we say about it?
The sum distributes normally.
Almost. In the limit. In the limit. So we have the central limit theorem that tells us that this sum will be normally distributed.
Between minus 1 and 1?
Normally distributed. Normally distributed. Normally distributed.
Well, we learned it like 5 years ago.
Okay. So we have the central limit theorem that tells us that this would be normally distributed. Okay, so let's so
And this is not equal to 3 or 4, right? For large.
well, you tell me.
I think so, that's a maybe from.
So what are the conditions for this to be? So I'll just write it down and then we go back to your question. So I want to argue that 1 over n sum over k of zk would be normally distributed with some mean and variance. Now the question here was, is it always true, or will it only be true when p is large?
If n is large enough,
So we have, if n is large, then this is sufficient because we sum a large number of elements. So this is sufficient for the central limit theorem. Okay, so it's normally distributed. What can we say about the mean? So the mean, well, the mean would be the mean of this. Okay? So, well, is it clear to everyone that the mean is 0? Yes, you have a question.
Not exactly the mean, because the sum is not over n, and we divide by n, so we don't normalize by amount. The normalization factor is smaller than the sum.
Are you arguing against the 0 mean, or are you arguing against the central limit theorem? Is your criticism related to this, or is your criticism related to this? Or both?
I think both, but this for sure.
This one?
Yeah.
Well, let's remove the 1 over n. Still, it will be normally distributed. I mean, just multiplied by n, or by n minus 1, or by whatever factor you want. So this would address your concern here. And here, well, the mean of this, I don't know how it's called in the fact that the sum of mean is equal to the mean of sums. So it's like a
Linearity of expectation. Yeah. Linearity of expectation.
Because of linearity of expectation, the mean of this is just equal to 1 over n sum of the means of these, which are plus and minus 1 with the probability 1/2, which is equal to 0.
this doesn't hold for p equals 2 if n is large enough?
Yeah, it does.
It does hold.
It does hold,
No,
yeah.
so it was okay even before.
Yeah, because n is large.
Yeah.
Yes. Okay, what can we say about the variance of this? Okay, you don't remember. So how are we going to compute it? N over 4. This cannot be true. I'll tell you why. Because it's independent of p. How can you come up with a result that is independent of p?
NC over
minus 1 double times minus 1.
Okay, let's do it. Let's do the math. It's not so difficult. Okay, so what's sigma squared? Sigma squared is equal to the average, and here I'm going to use notations of an average which are not non-standard. We have these double brackets, and I'll explain why in a sec, of well, of this term squared, right? Because the mean is 0. So we have here 1 over n sum over k zk squared double bracket. So the reason that I'm using double brackets is we will not care much about it in this course, but this denotes the fact that the average here is not an average over noise, dynamical noise in the system, or thermal noise in the system. Rather, it's an average over the realization of memory patterns, which is known as frozen noise or quenched noise. But for our purpose, it's just the notation of an average over realization of memory patterns. So this is what we need to compute.
N minus 1 multiple p minus 1 divided by 4 n squared.
Sorry, you're giving me the answer?
Yeah.
Can you repeat it?
N minus 1 have multiple p minus 1 divided by 4 and n squared.
Well, close, but not exactly. Let's do it. It's almost. Okay, so we can take the 1 over n squared outside because of not what was the name again? But this is not the linearity of expectation. This is the linearity of expectation that we can take the 1 over n squared out. Okay, 1 over n squared averaged over sum over k zk squared. Now the way to do it is the following. So we have an average of a sum. There are various ways of computing it. It's not so complicated, but just for the fun of it, let's do it. Well, not for the fun, just to learn the technique. So the way to do it is we have a sum. We have basically a product of sums. So this would be sum over k zk times another sum over k zk. Right? This is sum squared. Now, the k is just an index, right? So I'm going to use another index. To avoid confusing, I'll call the first one, I'll leave it as k, and the second one, I'll use another index. I'll call it k prime or something. And now I can use the linearity of expectation? No. There was this rule that I can take the sum out. It's 1 over n squared, sum over k prime of zk prime. All I did here was to take the sums outside the expectation, because expectation of sum is the sum of expectation. What? There's
But you turned it into
okay. I left the sum. I'm sorry.
These are all the linear operators, so you can do what you do.
I don't know what's the right terminology to justify it, but it's kosher. Okay, so what can we say about zk prime average? So we have 0, 1, more votes?
Oh, no. Half.
Half. 0, 1, half.
Because they're both 1. When they are multiplied.
1 over 4. We have 1 over 4. So 0, 1 over 4, 1 half, and 1. Well, let's think about it, okay? There are two cases. So there are two possibilities, okay? Let's say that k and k prime are indices. They go from 1 to n minus 1 times p minus 1. Now, on the way, zk and zk prime can be either the same or different, right? So what can we say about the case that they are the same? Well, when they are the same, we'll have here zk squared, which is equal to 1, because zk is plus minus or minus 1. What about the case where zk is not, where k is not equal to k prime? Well, let's do it in two steps. Okay, so there is a case where k is equal to k prime, and here we will have the average of the zk squared. This will be the first term, plus 1 over n squared sum over k not being equal to k prime, zk prime. So this we agreed is equal to 1. What about these terms? When k is not equal to k prime, zk and zk prime are independent. So this would just be equal to, so here we have n minus 1 times p minus 1 terms, n minus 1 times p minus 1 over n squared. This is the first contribution. Almost what you predicted, with the exception of the 4.
Yeah, I know why I'm wrong, because originally I calculated 0, 0, and 1, but it's 1 minus 1.
Right, that's the
So
reason.
that's
Okay.
4.
Plus 1 over n squared, sum over k different from k prime. And since zk and zk prime are independent, this would be equal to average of zk average of zk prime, which are both equal to 0. Which implies that this term that we're interested in calculating in the first place is normally distributed with 0 mean and variance, which is equal to n minus 1 times p minus 1 over n squared. So now we can start calculating the probability that this term would be positive, depending on n and p. And this is a good point to take a break. We will convene in 1:05.
computation בריבוע פחות computation של הריבוע. הממוצע בריבוע פחות הממוצע של הריבוע. הממוצע כן. אתה לא עושה את הממוצע אם היית מוסיף את הריבוע ביניהם, אם אתה מוסיף את הריבוע ביניהם, זה באמת האיבר השני. אם במקום גדול, זה היה ממוצע. כן, גדול לא, אבל הכנסת פה לפעמים של הסתברויות. אוקיי, אז ממוצע של משך מכפלה של משתנים תלויים היא כל המשתנים עצמם. כאילו התוחלת של משתנים מכפלה שלהם אז זה המכפלה של התוחלת.
כן, אוקיי, זה שווה ל-SI ושהוא תחליף את ה-SI
כן, שוב
כן, ראיתי, פריזם התעדלתיות. מצד שני נתנו לו עוד פעם לעבוד מולטי-סלר.
לפחות הוא קונסיסטנט. מה זה? הקבוצות לזה, לא יודעת אם זה
אם שווה ל-P, זה אומר שזה פיקס פוינט? כל SI שמקיים את המשוואה הזאת הוא פיקס פוינט. זה מההגדרה של זה, אתה דורש את DS ו-DT.
שזה שווה ל-0, זה שווה לזה, נכון?
כן, שזה שווה ל-0. אתה מקבל SI שווה ל-HJ, ו-G זה הפיינדר. אז כל תבנית שמקיימת את המשוואה הזאת היא פיקס פוינט. כן? ואז מפה אתה אומר, אז בוא נבדוק אם ספציפית ה-P הם מקיימים את הדבר הזה. זהו? תודה רבה.
כל זה שווה עיגול. מה זה עיגול? זה עיגול הזה? זה האפס. זה היה אחד הרגעים החדשים שלי בחיים. כאילו, תראה, הוא משתלט לי במלא נוטים שאני קראתי עיגול וכאילו, מה זה עיגול הזה?
כמו בבדיחה על קורס באינפי, ושאלו צריך חייב. כן, היה סבבה, רק לא הבנתי למה המרצה כותב את ה8 שוכב ואת ה3 הפוך.
אני כזה רגע, מה זה אומר? בוודאי.
עכשיו שאלת לנו בהתחלה שאלות על הסרטונים.
חצי אינסוף.
מה היה ההבדל בין הסרטון השני לראשון?
השני הוא רק היה צריך להגיד מה הוא זוכר מהסרטים, לתאר את הסרטים שהוא ראה.
וכשהוא אמר סימפסון, אותו נבדק, כאילו עד פעם זה התחיל להתחרפל שם? אוקיי, תודה.
אם זה לא, אתה חושב שזה לא היה ברור לאחרים, וזה הלב של אם זה לא היה ברור, אז עדיין נחזור על זה.
לא, למה? לא, החלק הראשון היה מספיק כדי לתאר את
אני חושב שהחלק השני הוא החלק המגניב באמת.
למה?
אפילו מתחילים ברבע לזה.
החלק הראשון זה חלק שאתה יכול לראות לעשות ניסויים בבעלי חיים, אין בעיה. אתה יכול להראות שיש סלקטיביות של נוירונים, זה לא חדש. החלק השני זה כשהוא חושב וספרי ריקול, שנזכר במשהו, אתה רואה את אותה תבנית כאילו. זה אתה לא יכול לעשות בבעלי חיים.
זה כאילו משהו יותר חזק.
יותר מגניב.
לא, זה כאילו קורלציה, כאילו...
הראשון זה היה כמו ג'ניפר אניסטון. השני זה מעבר לזה. שני אתה מראה שהוא חושב על ג'ניפר אניסטון, אתה רואה את זה. לא כשאתה מראה לו משהו, לא כשאתה נותן לו סטימולוס שמעורר את ג'ניפר אניסטון, שהוא really thinking about ג'ניפר אניסטון, זה נראה של ג'ניפר אניסטון.
אבל זה הקבוצה של הדאטה אנליסיס. כן, הם חילקו אותנו לקבוצות של... באמת? לא, כאילו, כל הזמן, לא קשור, לא קשור קונצפציה, זה לא... כאילו, עשיתי מדע סביבה. מה? כן. זה לא יודע קונצפציה שהיו. כן, זה קשור לקונצפציה שהיו.
Okay, so the question that we asked ourselves is, will a memory pattern be a fixed point of the dynamics? This is how we started. We wrote down the conditions for which the first memory pattern is a fixed point of the dynamics. And it turned out that the requirements are that this would be positive. Let's let's look at this term. So there is a term that is equal to 1 minus 1 over n, which is always positive and very close to 1. The limit of n goes to infinity. It would be equal to 1. And there is this term, and this term is more interesting because this term cannot be guaranteed to be equal to 1 because it's a stochastic variable. In the limit of large n, it is approximately normally, or in the limit it becomes normally distributed with zero mean and some variance. And the larger this variance is, the more likely it is that that this equality that we wrote here will not hold. And the question that we will ask ourselves is, what are the conditions such that it will still hold? So one trivial example would be the case of p being equal to 1. That's not very interesting. We will be interested in the case where p is large. So the question is, how large can p be in order for this to be a fixed point? So we can draw it. Is it okay that I will now? Thank you. How large can p be such that we will still be able, such that still the memory pattern will be a fixed point? So let's look at this term. So we are interested in sum over j, jij, pj1, this term, or more precisely pi1 times sum over j, pj1, sum over j, jj, pj1. And this will be normally distributed around approximately 1 with variance which is approximately equal to p over n. This is in the limit of n being large and p being large.
Why do you need p be large for this? Is it only enough for n to be large?
Well, I had this p minus 1.
Maybe n over p is larger than 1 should be the... No.
If there's one thing that I learned as a teacher, is that it makes sense first to draw the normal distribution and only then to draw the x's. Otherwise it's... Okay, so this is this term. This is I'm sorry, that's the x-axis. This is this term, and this is the distribution of this term. And this is 1. So this term is normally distributed around 1. And the probability of a mistake is this area where the distribution is the area in which the distribution is negative, right? So if this distribution is very narrow, the probability of mistake is 0, right? If this distribution is very wide, then the probability of a mistake is, probability that will be negative is half.
What is a mistake?
Well, probability that this would not be a fixed point. Probability that this would not be positive, and therefore this will not be a fixed point. Yes.
This is 1 minus p I 1.
Yeah, that's why it's 1, right?
This is not.
No.
No?
I don't think so.
Because of the sum is around 0.
But now you did
No,
1 minus.
I didn't write this sum. I wrote this term, the term that we were initially interested in, that had a plus 1 minus 1 over n, which n large n is equal to 0, plus this term. So the distribution of the entire thing is around 1 and not around 0.
Okay, that's right. So it means that up there you should have 1 minus or n minus.
Sorry, I don't understand your question.
Okay,
No, please ask.
So shouldn't you have like 1 minus p I 1 j?
No, it doesn't affect the thing.
Okay.
How does this term relate
We
to
only
this?
translate.
Yeah.
This is just this is a second term, and I added 1 minus 1 over n to it. So we'll just change the mean. We'll add 1 to the mean, or more precisely 1 minus 1 over n.
How does this relate to the term you wrote up
This
there?
again. So this is, and now I'm plotting the distribution of this.
Okay.
We previously computed this term, so now I just added 1 to it. This term is equal to this term. This is equal to this, to this, to this, to this.
With the 1 minus 1 over n?
In the limit of large n, 1 minus 1 over n will be approximately equal to 1. So we know that the width of this distribution will be approximately equal to p square root of p over n. Variance is p over n, so the standard deviation is square root of p over n. So we can so kind of a hand waving argument would be that this should be standard deviation should be smaller than the mean, or something like.
Half of the mean. Yeah.
Depending on how accurate you want to be. We will be more accurate in a sec. But like a hand-waving argument would be something like square root of p over n should be smaller than 1. Or if it is sufficiently small, then the probability of a mistake will be small. Or that p should be smaller than n. So the number of memory patterns that we embed in this network should be smaller than the size of the network. That's a hand-waving argument to computing something that we haven't described so far, which is known as the capacity of the network. Namely, the number of memory patterns that it can store and still retrieve. So any network will have a limited capacity, and we use this calculation to get a feeling on the number of memory patterns that we can embed in this network. Questions? Are there any questions? Yes.
So what do we take from this? Like if we demand this condition, so every pattern will be the fixed point of the model, right?
Yes.
For sure, for
What do you mean by guaranteed? You know exactly how to compute it. You know what's the probability that it will not. This has to be satisfied for every neuron in order for P1, the vector P1, to be a fixed point. And it has to be satisfied for every neuron and for every memory pattern if you want all the memory patterns to be fixed points. Now you may say that, okay, I don't care, maybe I have a mistake in one neuron in one memory pattern, maybe it's okay. So the question of how let's say stringent you are will depend on how much you care about mistakes. We will be more precise in a few minutes. More questions? Yes.
But what, even when C is equal to 2 and you have a very small possibility of this not being a fixed point, then how can you say it is different than?
No, I'm not saying. I'm saying that with a very high probability it will be a fixed point. How high? Well, you can compute it.
Like a fixed point is a property of the network.
It is a property of the network.
It depends on the specific input.
So the idea is the following. You generate 1 million networks. The networks differ in the particular realization of memory patterns. And out of these 1 million networks, the first memory pattern is not a fixed point. Are you satisfied as a thinking about it as a fixed point? If you are 3 out of 1 million, it doesn't work, and the rest it works. So it becomes the question of a fixed point becomes a probabilistic question, but not on the dynamics. The dynamics is still deterministic. It's on the specific realization of memory patterns. More questions? Let's be more precise. We can delete model. This is too much. I need a letter for probability. Now in my notes it's P. Right. Okay, let's use PR. So I'm going to define the following thing. PRI minus, okay, this is the probability that for neuron I, the equation, the fixed point equation, will not be satisfied. Okay, that's it. Probability that for neuron I, the fixed point equation is not satisfied. Okay?
Meaning this is not bigger than.
So meaning that we are here.
This is not.
So this would be equal to the probability that the noise is larger than, well, the contribution of noise is larger than -1.
Do you call noise?
This stochastic term. The probability that we are here. So this is just the probability that the normal variable is smaller than -1, given that the variance is p over n. So it's an integral dz over square root of 2 pi sigma squared e to the minus z squared over 2 sigma squared, where sigma squared is equal to p over n.
I'm sorry, I didn't quite get it. Like, why is the upper limit is -1, not 0?
Because he didn't do z -1, shifted it to 0.
Because I'm interested in the probability that this to be in this region.
You did the shift, right? You shifted the whole plot.
You could have wrote in until 0 and z -1.
Around 0?
No, yeah, maybe Jonathan can just explain for a second.
Okay. So there are two ways of thinking about it, which are mathematically equivalent. One is we can look at this distribution and ask what's the probability that this term will become negative. That's one way of thinking about it, which will be equal to an integral from -infinity to 0 dz over square root of 2 pi sigma squared e to the minus z minus 1 squared over 2 sigma squared. That's one possibility of looking at it. Another possibility of looking at it, which is mathematically identical, is to think about this normal distribution and ask what's the probability that the stochastic term or noise term will be smaller than -1. So think about the distribution that is a normal distribution around 0 and asking what's the probability that the variable will be smaller than -1, which is this integral. Now, replacing z with z prime, which is equal to 1, will go from here to here. Both of them are exactly the same and conceptually the same, everything is the same. Did I answer your questions? Is it clear? Good. So our goal now is to come up with a more precise measure than this one. This was like a hand-waving thing. Want something more precise. This would be equal to an integral from -infinity to -1 over sigma dz over square root of 2 pi e to the minus z squared over 2. This is just changing variables. So this is a probability. This is a probability of a mistake, again, that this fixed point equation is not satisfied for neuron I. Is it sufficient? No. Why not? Because this should be satisfied. This should be true. This probability should. We are interested in the probability of that there will be no mistake for any neuron. Let me say it again. This is a probability of that the fixed point equation is not satisfied for a single neuron. We want it to be small, but actually we want it to be much smaller because this should be true. This should be because the fixed point equation should be satisfied for all neurons, right? So this would only be true if this term -1 over sigma would be small, large, intermediate, or very negative. So 1 over sigma should be large. -1 over sigma should be large and negative, so that the integral would be small. So the reason that I'm doing this thing is to teach you how to approximate this integral in the limit of 1 over sigma being large. In the limit of sigma being much smaller than 1. This is why we're doing it. Because it's a very useful approximation. If sigma is very small, 1 over sigma is very large, minus 1 over sigma is very negative, and the integral is very small. So we are interested in this regime. So we want to approximate this integral in this regime. Okay, so how are we going to do it? This is a kind of it's kind of interesting. I mean, well, when sigma is equal to infinity, well, when sigma goes to 0, then this integral is equal to 0. So and we are interested in the limit of small sigma. So any suggestions on how to do it? So we have an integral that we want to compute. We know its value when sigma is equal to 0. And we want to compute it for small sigmas. Yes?
I'm not sure I'm gonna say what you want me to say, but I think we could just approximate this exponent function to like something that has expresses the tail of it, just to do like a Taylor expansion.
So to do something like Taylor expansion. Yeah. So in principle, we know the value of this integral when sigma is equal to 0, right? So now we can take this integral and
measure only the regime where it's very small, the exponent is very small.
Where we can just do a Fourier expansion of this integral for small sigmas. I leave it as an exercise to you to show that it will not work.
Fourier?
Yeah, to do Fourier here. Why will it not work?
Why should we think of doing it?
Well, you have a function, okay? You're interested. Why Fourier is the first thing to think about, okay? You have a function that you want to approximate. When one of the parameters is small. You know the value of the function when this parameter is equal to 0. So now all you need to do is Fourier expand it, and then you'll get an element that is proportional to, in this case, sigma, and then an element, if you want to be more precise, sigma squared, sigma cubed, and so on. To write it as a series. Sorry. Taylor. Sorry. Taylor expansion. I don't know why I said Fourier. Maybe because of the election in France. So I'm very interested in Fourier. No, sorry. I apologize. Taylor. I will remove 5 points from my final grade. 5 more points. So Taylor expansion. So you do Taylor expansion here, right? That would be the naive thing to do. It will not work. Why will it not work? You'll get 0. You'll keep on getting zeros, and it will become clear when we do it properly. Then it will become clear why it will not work. That's why it's worthwhile thinking about it. That's why it's kind of an interesting problem. Okay, so the integral that we're interested in is, let's write it here. The integral is an integral from minus infinity to minus 1 over sigma dz e to the minus z squared over 2. This is the integral that we're interested in. We just remove the 1 over square root of 2 pi. And now we will do integration by parts. So we will write it as an integral from minus infinity to minus 1 over sigma of 1 over z times z e to the minus z squared over 2 dz. Okay? This would be like the u and the v prime. So this term, an integral of z e to the minus z squared over 2 dz. How are we going to compute this one? Change variables. K is equal to something like a z squared over 2. So K is equal to z squared over 2. So this will be an integral of e to the minus k dk, which would just be equal to e to the minus k. So this is the first term.
Where's the z that is multiplying z?
I'm sorry? This is the v prime, just taking the integral of this one. Integration by parts. So the integral will be equal to minus 1 over z e to the minus z squared over 2 from minus infinity to minus 1 over sigma. This is the first term. Minus an integral from minus infinity to minus 1 over sigma of the derivative minus 1 over z squared e to the minus z squared over 2 dz.
Another minus. One minus.
Yeah, another minus. Which is equal to sigma e to the minus 1 over 2 sigma squared minus so what are we going to do with the next term? Well, we're going to use exactly the same trick as before. So this will be integral from minus infinity to minus 1 over sigma of 1 over z cubed z e to the minus z squared over 2 dz. Are you with me? So, yeah, so this is 1 over z squared, so I write it as z cubed times z. Well, why did I write it this way? To do integration by parts. And what we will get when we do an integration by parts, we'll get z to the power of 4, 5, 6, 7, 8, and 9, and 10, and so on. Right? So basically, the result will have the shape of sigma e to the minus 1 over 2 sigma squared, 1 plus something which is order of
Sigma to the third.
sigma squared.
Why?
Sigma
Sorry,
squared.
1 over.
No, sigma. The next term will be sigma.
Yeah. Sigma.
Why is it equal?
No, that can't be. This is already sigma.
No,
It's sigma to the
times.
Oh, okay, times.
Times.
Why is it equal order of sigma squared? Because.
So sigma squared, no? Because the next term will have sigma to the third.
Well, this
Here you
is
have
still
one
true.
over-
What I said is still
Yeah,
true,
it's
even
still
if you are
true.
right.
But the term is
Um,
even smaller. The next term is even smaller.
The next term will be.
Here you have 1 over
yeah.
z, and here you have 1 over z to the third.
Yeah. You're right. Okay.
Can you give an intuition about how you can tell the order of the integral?
Intuition about what?
About the order of the integral. Like how can you tell?
How did they? What was the trick? How did they do it?
No, how can you tell the order of it? How can you tell the order? Like for me.
Well, you do exactly the same thing as before. You integrate by part. That's why I wrote it this way. And then you'll have as before. You'll have the now you'll have the 1 over z cubed times. So you'll have you do the same thing as before, okay, for the v prime, and then you have the u, which is 1 over z cubed times this integral. And the next term you also do integration by part. Every time that you do it, you'll take a derivative, and then you'll integrate by parts again. And now, so the dominant term here is this one. This is a dominant term, and if you Taylor expand it, you get 0. That's why the idea of Taylor, not Fourier, Taylor expansion doesn't work here. Okay, so this is a probability that for neuron I, the fixed point equation is not satisfied. So this is a very useful limit. The tail of an error function, or the tail of a cumulative normal distribution function. So it's a very useful approximation in, I wouldn't say all aspects of life. This would be too much, but in science it's kind of useful. Also in economics, in finance, if you are interested in what's the probability of unlikely events, to quantify the probability of unlikely events, this is kind of a useful approximation. Okay, this is a probability that for neuron I, the fixed point equation is not satisfied. But what's the probability that the fixed point equation will not be satisfied for at least one neuron?
One minus
One minus d
and n. To the power of
to the
n.
power of, not the power into of P. N.
So this would be 1 minus, wait, it's kind of confusing, always confusing. It always confuses me. So this is 1 minus the probability that there will be no mistake in no neuron, which is 1 minus, let's call this probability minus. This would be 1 minus probability I minus to the power of n. So this is a probability of not making mistake for neuron I. This is a probability of not making a mistake for all neurons. This is a probability of making at least one mistake in at least one neuron, which can be written as 1 minus e to the power of n log 1 minus probability I minus, and we are interested in the regime of small probabilities, so we can Taylor expand log, which would be equal to 1 minus e to the minus of n probability I minus. Okay. So we want this to be small, right? We want this probability to be small. Well, how small? Now this is a question of how happy will you be with probability of mistake in 1 in a million, or 1 in 1,000, or 1 in a trillion. So we need to put some numbers here, but we can say that our requirement would be something like n probability I minus should be smaller than something. Should be smaller than a number, which I will call 1 over n. This is a requirement.
Requirement for what?
Well, we are interested in satisfying the fixed point equation. So in order for us to satisfy the fixed point equation, we want this to be sufficiently small. Well, how small? Again, it depends. But there will be an n here. You can put a number. N can be 1 or 2 or 3 or 7, but this would be something that depend on your probability, but not that much. N will keep on being order 1 independently of how accurate you want it to be. So it will not matter that much if you care about 1 in a million or 1 in a trillion or 1 in 1,000. This would be just adding, I don't know, going from n being equal to 3 to n being equal to 6 or 7 or something like that. So now we can start quantifying in a more precise way what are the requirements what are the requirements on the sigma, which is equal to square root of p over n. And this, I'm afraid, we will do on Thursday.